Thank you. So, good evening, everyone, and welcome again for the sixth live session for the course Introduction to Semiconductor Devices. As you know, this is being taught by Professor N.K. Emani from IIT Hyderabad, and I am Samadhan Kamble, your PMRF TA for conducting these live sessions. I am a PhD scholar at IIT Madras, working on the CMS experiment at Large Hadron Collider in experimental high energy physics area. So, as you know, the plan for the sessions from my side is as follows. So in the first 10 to 15 minutes, I'll briefly discuss this week's lecture content. That will be a quick refresher for you so that it will be helpful in the helpful when we solve the problems based on the assignment, and then we'll move to the assignment problems. Primarily, those assignment problems are from the previous courses offerings, but those are quite similar to your current set of assignments as well, and also to your end sem examination. So let us go to the summary first. Okay, so to summarize this week's content, I have 3 slides. So in the preceding 2 to 3 weeks, we have considered the PN junction and assumed that the semiconductor material was the same throughout the structure. This type of junction is referred to as the homojunction, and we also developed the electrostatics of the junction and derived the current voltage relationships. But in this week, what we have considered is the metal semiconductor junction and the semiconductor heterojunction, in which the material on each side of the junction is not the same. So these junctions can also produce diodes. So like a PN junction diode, a junction formed between a metal and a semiconductor has important technological applications, and depending on the work function of the metal and the semiconductor, the contact being formed can behave either as a rectifying contact or as an ohmic contact. So some of the key definitions to keep in mind related to the metal and semiconductor junctions, I'm going to just summarize here for you. So okay, so let us consider this metal semiconductor junction before and after applying the contact here. So there are different parameters of interest that will be helpful in the problem solving as well. So let me go one by one. First is the work function of the metal. So it is an energy required to remove an electron at the Fermi level to the vacuum level E0, which is outside the material, outside the metal. So it is also an invariant fundamental property of this specific material. So this is the work function of the metal. Then the electron affinity, so this parameter. So electron affinity is defined as the difference in energy between the reference vacuum level, that is E0, and the conduction band energy of the semiconductor, and it is also an invariant fundamental property of the specified semiconductor. So chi, which is the electron affinity, is given by E0 minus EC. Going to the third parameter, that is the work function of the semiconductor, that is phi s. So phi s consists of two distinct parts. One is the electron affinity, that is chi, and also the EC minus EF, this gap. So phi s can be written as chi, that is electron affinity, plus this gap EC minus EF. This energy difference, if you can recall, that is a function of the doping concentration. As you know that the Fermi level, that is EF, has the position which is as a function of the doping concentration. So we define EC minus EF separately as phi n. So phi s then can be written as chi plus phi n, where phi n is basically EC minus EF. Okay, so going to the fourth parameter, that is the Schottky barrier, phi b naught, and this is the parameter which is the ideal barrier height of the semiconductor contact, the potential barrier seen by electrons in the metal trying to move into the semiconductor. So this is the potential barrier from metal electrons in the metal region to cross into the semiconductor region. This barrier is known as the Schottky barrier, and it is given ideally as phi m minus chi. So phi m is the metal work function and chi is the electron affinity, and phi b naught, which is the Schottky barrier, is the difference between these two quantities. Then coming to the next parameter, that is VBI, or which is nothing but on the semiconductor side, VBI is the built-in potential barrier, and this barrier, similar to the case of the PN junction, is the barrier seen by electrons in the conduction band trying to move into the metal. So the built-in potential barrier is given by phi b naught minus EC minus EF. So this is the built-in potential, and as a function of the phi b naught and the EC minus EF value, which is nothing but phi n, can be written as phi b naught minus phi n. So this is all about the built-in potential. Now let us consider the last parameter, that is the space charge width, or the width of the depletion region as we know it. So the Schottky diode is identical to one-sided junction. So we also saw the one-sided junction in which the one of the side is heavily doped, so that the other side depletion region is such high that the depletion region on the doped side is negligible. So that is nothing but the one-sided semiconductor, so one-sided junction. And Schottky diodes are also can be approximated as the one-sided junction, and hence the depletion region is approximately equal to the depletion region on the n side. So this is the n side semiconductor here, and that, let me just add somebody. Okay, yeah, coming to the point. So depletion width, which can be approximated as the xn, which is width on the n side of the junction, that is n side n type semiconductor, is given by this particular relation, which is again the function of the built-in potential and the applied doping. So let us go to the slide number 2, that is short summary for short summary number 2. So we saw that the current transport in the metal semiconductor junction is mainly due to the majority carriers as opposed to the minority carriers in a PN junction. So as we know that the Schottky diodes are the majority carrier devices. So as I said, that the current transport in the metal semiconductor junctions is mainly due to majority carriers, in contrast to the minority carriers in the PN junction as we saw. So considering the case of rectifying contact, with an n-type semiconductor, the transport of electrons is over the potential barrier described by the thermionic emission theory. So what we consider here is the thermionic emission. Considering the thermionic emission theory, the net current density in the metal to semiconductor junction can be given as this particular relation. So the total net current density is given as J is equal to JST times exponential of EVA by KT minus 1, where VA is the applied voltage and JST is the reverse saturation current density, and the JST is further given as A star T square exponential of minus E phi Bn over KT. where A star is a constant, also called as the effective Richardson constant for the thermionic emission, and the phi bn, that is the Schottky barrier height, is the effective barrier height changed from phi b0 because of the image force lowering. So there are different effects that we saw. So one of them is the image force lowering, and because of that the Schottky barrier height is changed, and that is given by the E, that is given by the phi bn, which is the effective barrier height. Also, the ideal reverse saturation current density of the PN junction diode can be written as this. So in terms of the depletion constants, also the lengths, we saw we have the relation for the reverse saturation current density of the PN junction diode. So this is one of the formula that we will be using in the problems later on. So let us go to the final slide for the summary, and that is the Mos capacitors. So we saw the Mos capacitor, that is metal oxide semiconductor capacitors. So as we know that the metal oxide semiconductor capacitors are key elements in all of the Mos devices. One of the example is the MOSFETs, that is metal oxide semiconductor field effect transistors. So before going to the advanced topic, we considered the Mos capacitors, which is a two terminal device, and is actually at the heart of the all the Mos devices. So we saw that the with analogy to the parallel plate capacitor, Mos cap can be considered a similar device, with one metal plate being replaced by the semiconductor. So also we have different assumptions that when we consider an ideal Mos capacitor structure, it assumes few things such as the metallic gate is thick enough to be considered as an equipotential region. Also the oxide is perfect insulator. So that is also an assumption, so that the zero current is flowing through it. And also there are other assumptions like the semiconductor is uniformly doped and so on. So we consider the effect of the applied bias on the Mos capacitor, and we saw there are 4 different configurations that are possible depending upon the applied bias. So let us consider these 4 configurations. So let Vg be the DC bias voltage applied to the gate. So Vg is the DC bias voltage applied to the gate, that is the metal contact. And conceptually, the metal and semiconductor Fermi levels may be thought as of handles controlled by the applied bias. So let us consider the Mos structure with p-type substrate as shown in below. So you can see that this is a p-type semiconductor. As you can see, the Fermi level is close to the valence band. The application of the gate voltage Vg leads to these different biasing conditions. So let us consider each one by one. So first is the flat band condition. So in ideal Mos capacitors, or ideal Mos cap to be abbreviated, when Vg is equal to 0, that is when we don't apply any bias to the metal side, the Fermi levels of the metal and the semiconductor are perfectly aligned and no band bending occurs at semiconductor oxide interface. So there is no band bending when the applied bias is 0. So this particular condition is called as the flat band condition. Considering the second configuration, when we apply the Vg which is less than 0, so this is the negative biasing at the metal side, it lowers the Fermi level in the metal relative to the Fermi level in the semiconductor, and also causes the negative sloping of the energy band, as you can see in the figure. So this makes hole concentrations near the semiconductor oxide interface to increase. So this hole concentration near the surface you can see is increasing, or in other words we can say that the Fermi level is moving closer to the valence band at the interface. So this particular condition where the majority carrier concentration is greater near the oxide semiconductor interface than inside the bulk. So this concentration is greater than inside the bulk. So this particular condition is called as the accumulation. Going to the third condition, the application of a small positive voltage Vg that is greater than 0 places a positive charge on the gate, and which in turn repels the positive holes away from the oxide semiconductor interface, and it then exposes the negatively charged acceptor sides. So this situation where the electron and hole concentrations at the oxide semiconductor interface are less than the background doping concentration is known as the depletion. So this is about the depletion. And let us consider the last case, the inversion. So with larger and larger positive bias, so here we applied a small positive bias. When we apply larger and larger positive bias on the gate, the electron concentration at the surface, concentration at the surface increases and reaches a point where Ns exceeds the bulk, P bulk. So Ns becomes more than the P bulk. P bulk, and the surface region appears to change in the character from P type to N type. So initially it was a P type semiconductor we have considered, but because of this increase in the concentration, it has now changed from P type to N type. And this situation where the minority carrier concentration at the surface exceeds the bulk majority carrier concentration is referred to as an inversion. Okay, so this was for the P type substrate, P type semiconductor. The biasing regions in the N type device are reversed in polarity relative to the voltage regions in the P type device. So if you consider the N type also, so it will be exactly reversed. These voltages will be reversed, and for example, the accumulation in the N type device will occur at Vg greater than 0. So accumulation in the P type occurs when Vg is less than 0, but accumulation in the P type occurs when Vg is greater than 0. So that is the thing that you need to keep in mind. So I think this forms a quick and nice summary. So let us move directly to the problems now. Till now, do you have any doubt? Otherwise, we can proceed to the problem solving. Okay, I consider it as no. So let us go to the problems. So this is the problem number 1. So this is a problem having a common data. So this is common data for question number 1 and 2. So I'll read out the data for you. 3 Schottky barrier diodes A, B and C are formed on N-type silicon with doping concentrations given as 10 to the power of 15, 5 times 10 to the power of 15 and 10 to the power of 16 per centimeter cube respectively. Assume a barrier height 5B0 of 0.65 volt, the energy band gap of 1.1 electron volt, and the intrinsic charge carrier concentration as 1.5 times 10 to the power 10 per centimeter cube, and the KT value as 25.9 milli electron volt. So the first question is to determine the phi n. So as we have seen in the summary slides, if you can recall that the phi n is nothing but the difference between the conduction band and the Fermi level. So phi n is nothing but EC minus EF. Okay, so we need to find EC, we need to find EF. EF is not given, but for different concentrations we have for EF is, if you can recall, that EF is given as EI plus KT over Q ln of ND over Ni. So this is for the EF we have substituted here. If you just solve the bracket here, we will get EC minus EI minus of KT over Q ln of Nd over Ni. So Ec minus Ei is nothing but Ec minus Ei. So this Ec minus Ei, that is this value, is nothing but the half of the band gap. So band gap is given as 1.1 electron volt. So Ec minus Ei, which is half of the band gap, is nothing but 0.55. And let us substitute the value of different parameters. So we'll have 0.0259 times ln of, let us consider one concentration first. So that is 10 to the power 15 divided by Ni, that is the concentration, intrinsic charge carrier concentration, that is 1.5 times 10 to the power 10. So if you just solve this, you will get the value of phi n for Nd equal to 10 to the power 15 centimeter cube per centimeter cube. Will have the value of phi n as 0.26 electron volt. So similarly, we can find out the value of phi n for other concentrations, that is 5 into 10 to the power 15 and 10 to the power 16 per centimeter cube. And I think that will be quite straightforward, just putting different values of Nd. So I'll directly give you the answer for this. So the phi n for three different cases is this. Phi n for Nd is equal to 10 to the power 15 is 0.26. Phi n for Nd is equal to 5 into 10 to the power 15 is 0.22, and phi n for Nd is equal to 10 to the power 16 is 0.20. Okay, so if you don't have any question, let us go to question 2, which is based on this common data again. So the question 2 is as follows: choose the correct option for the built-in potential VBI in the three devices. So again, going to the recap slide, we know that our built-in potential is the difference of the phi b naught and phi n. So VBI is nothing but phi b naught minus phi n. So also we know that the phi n is Ec minus Ef. So we know that this value, that is Ec minus Ef gap, is a function of the doping concentration. So as we increase the doping, we know that the Fermi level moves further inside, moves further closer to the conduction band, and hence the phi n value decreases. So as we can see in the problem given here, that the concentration is being increased, so the value of phi n is going to be decreased. So phi n for C will be less than phi n for B, which will be less than for phi n for A. So given all these information, can anyone tell me what should be the answer for this question based on this equation and based on this information, that the phi n for these three cases is in this particular order? You can just unmute
B,
yourself.
Option B.
Option?
Sorry, option D.
Option D, you are saying 1, 2, 3. This option, right? Yeah, so this is indeed the correct option. So we can see that the value of phi n is, as we go on increasing the concentration, it decreases, and as it decreases, the value of VBI will increase because the subtractant will be reduced here. So the built-in potential in three cases for three devices based on the depletion, based on the doping concentration, is given by this particular relationship. Okay, so let us go to question number 3 directly. So this is a question. Okay, so I'll read out for you. A PN junction diode and a Schottky diode have equal cross-sectional areas and have forward bias currents of 0.5 milliamperes. The reverse saturation current of the Schottky diode is given, and that is 5 times 10 to the power minus 7 ampere. The difference in the forward bias voltage between the two diodes is given, that is 0.3 volt, and we have asked to determine the reverse saturation current of the PN junction diode. Okay, so we know that from our recap slide that the total current density is given by this particular equation, that is J is equal to JST, that is the saturation current density, times exponential of QVA by KT minus 1. Okay, so the total current for the Schottky diode is given as 5 times forward bias current is given as 0.5 milliampere. So let us substitute the 0.5 milliampere here. So 0.5 milliampere, and also the saturation current is given for the Schottky diode, that is 5 times 10 to the power minus 7 ampere exponential of QVA by KT minus 1. So from this we can find out the value of VA. So if you just rearrange this equation, so let me do it for you. So 0.5 times 10 to the power minus 3 divided by 5 times 10 to the power minus 7 and plus 1 will be equal to exponential of QVA by KT. So therefore, if you take the ln on both sides, the exponential will get cancelled. So VA will be KT by Q times ln of, if you just rearrange this, just a moment. Okay, if you just rearrange it, it will be 10 to the power 3 on the numerator. So 10 to the power 3 plus 1, that is 1001. So KT by Q, if you can substitute here, we'll get the value VA as 0.1789 volt. Okay, so VA we have got, and they have said that the difference in the forward bias voltage between two diodes is 0.3 volt. So we know that the PN junction has higher threshold voltage, so higher threshold, so it uh, uh, turns on at higher voltage, so hence the larger VA needs to be applied to get the same current. So VA in case of the PN junction, so VA for PN junction would be the VA for the Schottky diode plus the difference, so 0.1789 plus the difference, that is 0.3, that is nothing but 0.4789 volt. So we got the VA for the PN junction. Now we can determine the reverse saturation current for the PN junction diode. So let me use this equation and solve for the reverse saturation current for the PN. So if you can rearrange equation number 1, so JST for the PN junction would be equal to the the total saturation current, that is 0.5 milliampere divided by the exponential and this factor. So if I just substitute those values, exponential of the VA is nothing but 0.4789 divided by KT over Q, that is 25.9 milli electron volt, that is 0.0259 minus 1. So if you just solve this, you will get the value of the reverse saturation current for the PN junction as 4.0 66 picoamperes. So pico stands for 10 to the power minus 12 amperes. So the answer is 4.64 times 10 to the power minus 12. So this is the answer for question number 3. Let us move then to the question number 4. Is it okay?
Okay, sir. Okay, sir. Thank you, sir.
Okay. Okay, so going to the question next. So this is again a common data for question number 4 and 5. So I'll read out it for you. Consider the equilibrium energy band diagram for an ideal metal semiconductor contact as shown in the figure 1, and answer the following questions. So this is the metal semiconductor contact band diagrams shown, two band diagrams A and B. So based on this figure we have to answer question number 4 and 5. Okay, so the question number 4 is, choose the correct option for the relation between metal and semiconductor work function for band diagram in figure 1a, and similarly the correct option for the relation between the metal and semiconductor work function for band diagram in figure b. Okay, so let us analyze these figures. So can anyone tell me which is the substrate here, or which is the substrate on these sides? Which is the semiconductor type here?
A is formally stopped, so it's N substrate.
Yeah, exactly. So this is the N substrate. So you can yeah, okay. So you can see that the majority carriers, that is electrons, because this is an N type semiconductor here. So the majority carriers are depleted here. The majority carriers are depleted. Majority carriers are depleted here, which are electrons, and this can also be considered as the rectifying diode. So if you draw the vacuum level, let me just draw, let us call it as the vacuum level, and so this is the work function for the metal. This is EFM, and this is phi s EF for the semiconductor. So the electrons move into the metal, depleting the semiconductor. So it is the depletion regime. So electron from the semiconductor, in order to make the Fermi level same, move from the semiconductor to the metal side, and which depletes the semiconductor side. So from this we can see that the phi m is larger than phi s because of the depletion condition. And if you consider the figure B, here the accumulation of the majority carriers has occurred. So accumulation of majority carriers, and so majority carriers which are electrons in our case. So this also can be considered as an ohmic contact. So if you just draw the vacuum levels for the B case, it will be the opposite of the case we saw for the figure 1a, and in this case electrons will flow from the metal into the semiconductor. Hence this will be also called as the ohmic contact. So we can see that the phi s is greater than phi m for B case. So phi s is greater than phi m for B, and phi m is greater than phi s for A. Okay, so we are running a little short of time, so let us move to question number 6. So this is also again a common data question. Let me read out it for you. Consider a tungsten barrier on silicon with a measured barrier height of 0.67 electron volt. The effective Richardson constant is given as 114 ampere per K square centimeter square, and also the temperature as 300 Kelvin. Also the data is given for the silicon PN junction. The different parameters at T is equal to 300 Kelvin are given. So let us go to question number 6. The objective of the question is as follows: calculate the ideal reverse saturation current densities of a Schottky barrier diode and a PN junction diode. So we need to find out the reverse saturation current densities for both the Schottky barrier and as well as the PN junction diode. So again, recalling from the summary slide, we have for the Schottky diode the saturation current, reverse saturation current given as A star T square exponential of minus E phi Bn by Kt. So if you just substitute all those parameters like A star, temperature, the value of phi Bn given as here, and the Kt, so just substituting here 114, that is A star, times 300 squared times exponential of minus 0.67 divided by 0.0259, will get the reverse saturation current for the Schottky diode as 5.98 times 10 to the power minus 5 ampere per centimeter square. So this is about the saturation current in reverse saturation current in the semiconductor Schottky diode. Let us consider the ideal reverse saturation current densities of the PN junction. So again, going to the recap slide, we saw that the ideal reverse saturation current density of the PN junction diode in terms of these parameters is given by equation 9. So directly we can substitute for the equation 9, we'll get the reverse saturation current for the PN junction as if you just substitute all those parameters in the equation number 9. I'm just substituting out it for you. (1.58 times 10 to the power minus 3 plus 1.6 times 10 to the power minus 19, that is the electronic charge, times 10, which is the dP, times 2.25 times 10 to the power minus plus 4 divided by 1 into 10 to the power minus 3. So if you just calculate this algebra, we'll get the reverse saturation current for the PN junction diode as 3.66 times 10 to the power minus 11 ampere per centimeter square. So we can note one thing, that the ideal reverse saturation current density of the Schottky barrier junction is orders of magnitude higher than that of the ideal PN junction diode. For the Schottky diode, using similar parameters, we can see that there is almost 10 to the almost 6 orders of magnitude difference between these two values. And that is one thing to keep in mind. Let us go to the question number 7, which is based on again the data given on the previous slide. So the question is as follows: calculate the forward bias voltage required to induce a forward bias current density of 10 ampere per centimeter square in a Schottky barrier diode and a PN junction diode. So we need to calculate the voltage required to induce the forward bias current density. So this amount of current density we need to induce, and we need to find out the voltage required for this in the Schottky barrier diode case and also for the PN junction diode case. So again, we know the the total current density for the Schottky diode given by the same equation that we have used for quite few times now, by kT minus 1. So we need to find out this voltage VA. So if you can just ignore minus 1 as compared to the exponential value, we can rearrange for the VA, this particular relation we can rearrange for VA as VA will be equal to the KT by Q will come here, KT over Q, and if you just take the ln on both sides, we'll cancel the exponential and it will simply be J over JST. So this is the value of the forward bias voltage required. Now let us substitute the values and we'll find out the forward bias voltage required in the Schottky case first. So KT by Q we can substitute as 0.0259 times ln of the forward bias current they have asked is 10 ampere per centimeter square, so 10, and the reverse saturation current that we calculated for the Schottky case was 5.98 times 10 to the power minus 5. So substituting that here, 5.98 times 10 to the power minus 5 will get the value of voltage required as 0.682 volt. So this is the voltage required to induce the forward bias current of 10 ampere per centimeter square in the Schottky barrier case. So this is for the Schottky. Let us do the similar case for the PN junction diode. So this formula we can apply for the PN junction diode as PA given as VT, that is temperature, ln of J over JST for PN. So again, just mere substitution. J is 10 and we know that the JST value for PN junction that we calculated in the last problem is 3.66 times 10 to the power minus 11 ampere per centimeter squared. So we'll substitute it here, 3.66 times 10 to the power minus 11. So we'll get it as VA for the PN as nothing but 0.682 volt. I'm sorry, this is 0.312 volt for the Schottky case, and this is 0.682 volt for the PN diode case. So again, one thing that you can note here, a comparison of the two forward bias voltages shows that the Schottky barrier diode has a turn on voltage that in this case is approximately around 0.31 volt, smaller than the turn on voltage of the PN junction diode. So we saw that the graph of I versus V, so if the turn on voltage are drawn here, so this will be the turn on voltage for the Schottky diode and this will be for the regular PN junction. So the turn on voltage for the Schottky barrier diode, as you can see here, is much lesser than for the PN junction diode. Is it clear? If yes, we can move to question number 8. Otherwise you can stop me at any time. Okay, so this is the question. So based on the problems that we have solved so far, I think all of you can answer the question for me. So I'll read out the question. Choose the correct statement or statements from the following statements. So one by one, if you just go for these statements, we will be able to say that if it is a correct statement or not. So let us go to the first statement, that is the Schottky diodes are the minority carrier devices. Can you tell me, is it true or false, or is it correct or wrong?
False. False.
Okay, so if it is false, then we can see that the Schottky diodes are the majority carrier devices. So this is one option. So this is a wrong option. Going to the second, the metal semiconductor diodes have much higher saturation current densities or much lesser diode saturation current densities. Can you tell me? We just saw in the previous problem here that the saturation current densities for the Schottky diode and the saturation current density for the PN junction diode. So if you just can compare these two also, so you can see that the saturation current density, reverse saturation current density for the Schottky diode is much higher, or the orders of magnitude higher than the PN junction diode. So this is indeed a true statement. Also, the Schottky diodes are high-speed devices because of all these parameters as compared to the PN junction diodes. And also, we saw in the previous problem that the metal semiconductor diodes have higher turn on voltage or the lower turn on voltage, and the answer is the metal semiconductor diodes have much lower turn on voltage than compared to the PN junctions. So this particular figure we saw that the turn on voltage for the Schottky metal semiconductor junction is lesser than for the PN junction diode. Is it clear? Do you have any doubt in this?
So
So there
what
are,
about Mos Capacitors?
yeah, metal semiconductor diodes, they actually form Mos capacitors only when we have the third element present, that is the oxide layer in between. So here you can see the Mos capacitor is shown. So metal and semiconductor is there, but in between there is oxide layer. So it is just not the metal semiconductor junction, it is the metal oxide semiconductor sandwiched together.
Okay, sir.
Okay, so let me go to the question number. So this is actually the last question. So this is the data for last two questions. So I'll read out it for you again. A simplified band diagram is given. A band diagram for the Mos capacitor is given as shown in the figure here. So we need to match the energy band diagrams labeled 1, 2, 3 with the corresponding substrate type and also the applied gate voltage and the bias condition. So again, this is we have seen it for at least couple of times in the problem solving. So let us go to question number 9, and I want you guys to answer this. So the question here is as follows: identify the type of substrate and thereby the Mos capacitor for each of the band diagram. So one piece of information that I can share here is that the nomenclature for the Mos capacitors is based on the inverting the charge, which is the inversion charge. So for the N Mos cap, the inversion charge is electrons. That is, and once the inversion charge is electrons, the inverted charge is electrons. That means it was inverted from the holes, and for holes to be the majority carriers, we need the substrate to be a p type. And similarly, for the p Mos cap, the inversion charge is p, that is holes, and for holes to be the inversion charge, the substrate has to be n type. So keeping this piece of information in mind, identify the type of substrate and thereby the Mos capacitor for each of the band diagram. So can you unmute and tell me that which of the type of substrate in these three cases, and hence which of the type of Mos cap is there in these three cases?
First one is accumulation mode with
Just tell me
negative.
which type of substrate is this, which type of substrate is this, and which type of substrate is this.
Where is the Fermi level? Fermi level mark. It's not marked.
Yes, so
Fermi
which
level is down.
yeah, so just tell
P
me
type.
which. Yeah, so this is a P type, this is N type, and this is
N
again P type. So because it is a
type.
P type, the inversion charge will be N type and it will be a N Mos cap. This will be N Mos cap. The type of substrate is P type. Going here, the type of substrate is N type. The inversion layer, inversion charge will be P, that is holes. It will be a P Mos cap. Going here, this is the substrate is P type. That means the inversion charge is electrons. That means this is an N Mos cap. Okay, so P type, N type, P type. So the correct option for this is, okay, let me see, it is E option. So P type, N type, P type. So P type will have N Mos, N type will have P Mos, and P type will have N Mos respectively. So this is the correct option for question number 9. Let us go to question number 10, which is the final question based on again the same data. Here we need to identify the sign of the applied gate voltage Vg and the bias condition for each of the band diagram. So the sign of the Vg and the bias condition, or the regime in which the particular configuration is in, so that we need to find out. Okay, so if you go to the figure number 1, you can see that the majority,
Negative with accumulation.
yeah, we can see that the majority carriers are the holes here and they have accumulated here, and for the holes to accumulate here we need our Vg to be negative. So once we applied negative bias here, then only the holes can accumulate, which are the majority carriers. So this is accumulation. Going to figure number 2, you can see that the N type is this. So the majority carriers is again accumulated here. So Fermi level is getting closer to the conduction band. So for electrons to accumulate in this region, we need Vg to be positive. So Vg is more than 0, and this is also a accumulation configuration, accumulation regime. And going to the third case, you can see there is an offset being formed here, and this is indeed the inversion layer. So even for the P type substrate, it looks similar to the N type. So we can see that this particular region has inverted from P type to N type. So this is indeed an inversion, and for large amount of electrons to accumulate at the oxide semiconductor region, we need large positive voltage here. So Vg should be very high than 0, and that will give us the inversion condition. Inversion. Okay, so the correct answer is AAI, negative positive positive. That is option C, negative positive positive, accumulation and inversion. Okay, so I think do you have any doubt, anything that you would like to ask, or any comments?
So with respect to last week, Our avalanche breakdown and Zener breakdown both are same. Their band diagrams are look similar.
For avalanche
They're
and
both
Zener, you are saying?
Zener breakdown. Yeah.
Yeah. So as we saw that there are two different types of breakdown mechanisms. So Zener is the breakdown mechanism, and avalanche is also another mechanisms. But these are quite different. Their mechanisms are also different. One is because of the reverse voltage applied, and another is because of the higher kinetic energy gained by the charged particles, majority charged particles. So these are two different mechanisms. So what you are asking?
They both energy levels look same or different. Their band diagrams look similar or different.
Yeah. So their band diagrams is for the breakdown. So band diagrams looks different in both cases because their mechanisms is the intrinsic mechanism is indeed different. So in the previous week, I also had a band diagram. So if you can go back to that slide, you can see the band diagrams, or you can go to the Niemann's book also. They have explained quite nicely how the band diagrams change for the avalanche as well as the Zener. Or if not, I can get back to you in the next week as well.
Okay, thank you.
Okay. So if there are no further questions, I would like to thank you all for joining for this live session. So thank you so much everyone for joining for this live session number 6, and I hope to see you in the next live session, that is live session number 7, scheduled on the 9th September at 6 p.m. Indian Standard Time. Meanwhile, you can go and check out my YouTube channel where I'll upload these recorded live sessions in case if you could not join because of any reason, or uh, you need some further clarification. You can go to the NPTEL course site, and in the discussion forum you can ask questions as well. So thank you again for joining, and I hope to see you in the next live session. Thank you. Have a nice weekend. Bye bye. Thank you.
Okay, sir. Thank you, sir. Thank you so much, sir.
Thank you so much. Thank you. You're welcome.